Okay, so like I said, we're going to talk a little bit about just the uses of Newton's laws in minor detail, and some of these things we've already talked about, so that's why I said I'm not going to go into major detail. And so you have some notes in front of you. You can make notations, you can highlight, you can do whatever you want as far as those go. But I tried to make some key points so that when you get ready to take your test, which is tomorrow, which you have your review for, that you can go through and, there are some key points to help you with your review on this. So we already did the Buckle Up Lab, which talks about car crashes. I went through and on these notes, I highlighted the 3 points of where you see Newton's 3 laws in the car crash. So we did that Buckle Up Lab, and Barbie went flying. Poor Barbie, or generic Barbie, I guess, because, I don't spend the money for real Barbie. So where do you see Barbie flying on, where do you see Newton's 3 laws on, for Barbie? So the first one, hopefully you saw that she was flying out, so the object in motion stays in motion, so she flew out of the car. The second one, there's a external force on the passenger because of the mass of the vehicle multiplied by the acceleration. The third law, in a car crash, the action force are the cars rolling with each other, and the reaction force is the force sent back due to the collision, which causes damage to the car. So there's basically to show you a demonstration of, in a car crash, where do you see all of Newton's 3 laws? Okay? Now, on top of that, when a car crashes, we talked about in Chapter 2, we talked about this concept called momentum. Momentum is, the mass of an object times its velocity, and that momentum is transferred. There's also this law called the law of conservation of momentum that says that momentum is never lost.
It changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth. Before the skydiver jumps, the floor of the plane provides a counterforce, which balances the downward force of gravity, right up until the moment she steps out. Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance.
So notice the two are starting to
The
equal.
upward force of the air equals the downward force of gravity.
So notice
When
the
forces are
speed.
balanced, the speed remains constant.
It's balancing out, so now that skydiver has reached terminal velocity.
She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea. To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea.
So you can see, though, with all the situations about how, like, initially the skydiver's at free fall because gravity's at most, and then it goes into, air resistance is pushing up, and then you've got the situation where they hit terminal velocity where the two forces are equal, and so all those situations are in play. So it shows you all those different scenarios. So that's why I really like that video, because I think it's a very good visual. Oh, thank you. Yeah, that's really big, isn't it? Is weightlessness. A lot of people think when you go into space that as the astronauts are traveling outside of our planet, that they are actually truly weightless, meaning that they are without gravity. The truth is that they actually have gravity. They actually have a percentage of our gravity. In fact, they have almost like 90-something% of our gravity. The reason that they appear to be weightless is because they are in free fall. They are falling. The shuttle is falling towards the Earth. They are falling at the same speed or same acceleration as our gravity. And so since they are doing that, and they are falling at the same speed as gravity, they are given the sensation that they are weightless. So since they're traveling so fast, and they're traveling so fast that they're traveling at the same speed of gravity, it's giving them the sensation that they are weightless. That's why that we can simulate weightlessness on Earth by taking plane rides where they just shuttle them up so fast or shuttle them down so fast that it gives them a sensation of weightlessness because they just travel at the speed of gravity. I also have another short clip. Here it talks about weightlessness. That might be better to understand than what I'm saying.
Have you wondered what it would be like to be an astronaut floating around in the space station?
But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating?
No gravity.
No gravity.
Zero gravity.
There's no gravity.
The stuff that holds us to the planet where we spin doesn't happen up there.
Gravity holds you to answer in space, there's nothing there, so you just float.
There's no gravity in space.
No gravity, there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So, where would the space station fit in this picture?
Can you give me a roughly the scale model of the Earth and the Moon? And then we're going to position the space station in there. So about like that?
Yeah, about that.
Closer. About there.
You ready to see the real distance? What do you reckon?
Oh, okay.
It's actually about here. Maybe a little further.
I think we were wrong.
Now, if the Moon is here and the Earth is there, whereabouts would you put the space station?
Yeah.
But here,
About halfway? Yeah. Right about here? So that's maybe like a quarter of the distance to the Moon. Let me show you the real distance. You ready for the real distance? The space station is right about there.
Oh, okay.
Right there.
Close.
There you go.
Real good.
The space station is actually only about 400 kilometers away. So, if you're in Sydney, it's a little further than the drive to Canberra.
But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
There's not much they float. We've seen them.
Well, clearly there's not. They're floating around.
I know they float. And the question is why?
No idea. I'm really confused.
Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here?
The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them.
If the Earth didn't put a gravitational force on them, they would flab into space. Surely. So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they...
They would still feel weightless until you smash into something.
So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
Okay. So that hopefully gives you a better idea of like what does it mean to be weightless versus, you know, hopefully the original idea of, you know, a lot of people think that they have no gravity in outer space. So hopefully that idea is kind of thrown out the window now, because we all know that they're in free fall. They're just falling at the same acceleration as gravity, and so that gives them the sensation or the experience of being weightless. So the last kind of topic of an experience where you see Newton's laws in action is rocket propulsion. Rocket propulsion is an example of where you see Newton's third law in action. And so the thrust of a rocket engine is an action-reaction experience. So in a rocket engine, the exhaust is your action, where you get the reaction of the thrust of the rocket being pushed off. So there is another real-life example of Newton's laws in action. So hopefully going through several... Incorporated, exactly. So, all right, so...